So if you start from first ellipse here, whose major axis is horizontal, and a copy of it rotated about its center O by 90 degrees. So I have these two ellipses here. I'm going to use this one here as the incidence ellipse on a Poncelet iteration, and I'm going to use the upright one as the caustic or the tangent ellipse. So it looks like for an aspect ratio of both ellipses of a number that was manually adjusted here with GeoGebra, and I don't have more resolution to adjust here very easily, adjust this aspect ratio, but it looks like if the aspect ratio of either ellipse is a number close to, and it might be exactly that number, to the golden ratio, 1 plus square root of 5 divided by 2, 1.618. It looks like this number here is really that number. You know, it's wrong here because I adjusted it manually. But if you do that, you get this wonderful result that you get a family of triangles interscribed between these two ellipses with golden ratios as their aspect ratio. Now what I'm also showing here is a set of interesting phenomena. So you have this family of triangles, so I can compute triangle centers. So here I'm showing the incenter. It looks like the incenter is following this curve, which, if our previous remarks were correct, cannot be a conic. It looks like a conic, right? But it has an interesting property that it seems to be going through the focus. So this is probably a curve whose degree is higher than 2, but it has this interesting property that it goes through the focus, right? Of course, you can construct identical families in each one of these lobes here, okay, these 4 lobes, but this is trivial. It's just a symmetric kind of construction, so we're not going to talk about it here. GeoGebra is also continuing this locus here, and you should ignore that, and you should ignore this one on the side here. And this is happening because at some crucial point you lose this construction, okay? So yeah, you lose it. So let's ignore that. But it looks like we have this x1 locus. It's kind of a curve segment, and it'll be interesting for us to determine which curve is this. Is it a degree 4? Is it a degree 6, or even higher? And also to show that it passes through F. In other words, there is a position here where x1, and that's quite an interesting thing, right? x1 is exactly at the focus. Okay, so let's look at the barycenter. Now the barycenter is not being properly shown here. You know, there's a problem with the locus algorithm, but it looks like it's, you know, it's this curve, this little arc of a curve here. I would ignore this other wavy part because the triangle degenerates, but whatever is in between those two extremes there, this could be a lower degree curve, okay, such as a conic. It probably will be a conic, an arc of a conic. So just this little arc over here. When I say it's likely a conic, it's because there is a result that says that x2 always follows a conic for an arbitrary Poncelet pair. Okay, now let's look at x3. x3 is over here, and it's only showing a very, so this is the circumcenter, right? The locus algorithm can only draw that little thing, so let's go ahead and move forward to see if we find any other gems here. These dotted, this sort of salt and pepper noise here, has to do with the locus generation algorithm, and because of these instabilities, you get this dispersion. But ignore all of this. The only thing we care about is this little curve arc here. Okay, now let's go to x equals 4. Oops. X equals 4 is out here. Doesn't look that interesting. Okay. I'm going to get to one that does look interesting. So 5, 6. Okay. Let's go ahead and skip that. Nothing here on the symedian point that is worth of note. Gergon point. Gergon point, not interesting either. We go to x8. Then we hit the Mittenpunkt. x10, we don't care. This one I thought it was kind of interesting. So this is Feuerbach. for your back point. Now, is there any chance that this could be the arc of a circle? That would be interesting, right? Let's go ahead and just do something visual here to see if there is a chance that this is the case. I'm going to go ahead and try to draw circle. There you go, through 3 points, or maybe a circumcircular arc, right? Let's go ahead and do this. I'm going to use the point as one thing, and then let's just get another point here on the locus, something like that. Yeah, it looks like there is a chance, although I'm kind of detecting a little bit of a deviation from the arc. Let's see here. Yeah, you can see this is not a circle. This is not a circle. So X11 is circle-like, but it's not a circle. So let's get rid of this last construction. And I'm back at X11. Now it's an interesting locus nonetheless. It's just that it's not a circle. It would have been kind of a miracle for it to become a circle. But let's keep going. X12, 13. I want to get to X20. This is 14. It looks interesting, but it's not, because you can see here that it's actually slightly overshooting. It looks like it's a nonlinear beast, okay? Or a non-circular beast. Here's X15. X16 becomes these two interesting external lobes. Actually, just one, right? I mean, we should ignore the one on the right, because that's probably an artifact of the locus algorithm. Okay, but you can see here, probably nothing too hot. Let me move this to the right a bit. Okay, and then we're getting to where I want to get, which is X20. Now, X20 is, I could be wrong, but visually, this thing looks like a straight line. Okay, so this would be kind of a miraculous thing, right? X20 is related to X4. It's a reflection of X4, if I'm not mistaken, about X3. Okay, something of that sort. I would have to look it up. But this could either be a pretty flat curve or a straight line. So, you know, we can do a visual test here by trying to draw a line between 2 points. So let me get this guy and that guy. And then let's just go ahead and do a zoom here. It looks straight, right? But this is too short a segment for us to determine that. Let's see if there are any distortions. Oops. If I move this point here a little bit. Yeah, just to see if there's... It looks pretty straight to me. But again, the jury will be out because as we saw, X4 and X3 don't look that great. So let's go back here. Let's do some undos. So I go back to the scene that I had before. That one, right? So if you go back, for example, to X4, which is constructor of X20, you can see here that it's slightly curved. When you move over to X20, you get something that looks like a straight line. And it could be the case that it is. And that would be an interesting proof or observation, right? I could keep going, but I haven't really seen anything too interesting going up. You know, and these triangle centers are less discussed, okay? And I'm sure that if I kept going until, you know, I don't know, X100, I would find something interesting, okay? But I think the two cool results here are that, or three cool results. First of all, at an aspect ratio, which is probably the golden ratio, you can close a family of triangles between these two identical ellipses with a 90-degree rotation for the caustic, right? A second observation is that X1 is some high-degree curve. We think it cannot be a conic because this pair is not confocal, and this is one of our observations from the past. So we think that X1 can only sweep a conic if a pair is confocal. This is not a confocal pair. Yeah, this would be interesting, right? And then the fact that X1 passes through F1, through the focus, can this be shown to be the case? In other words, all we need to do is to show that in this symmetric position, the x1 of this triangle is a focus, right? And then the other potentially harmonious thing is that called the Longchamps point, x20? I believe it is. Looks like a straight segment perpendicular to the major axis of the incidence ellipse. Okay, so that's all I have. See you on the next video.